don't worry, I'm not trying to give you trouble, but I want you to learn. Now, we talk about the on-off states, but now we are not satisfied with that when we go to subthreshold region. Let's look at the drawing of a transistor again. Maybe you can tell me what I'm drawing. So what is this box, by the way? Do you know when I'm trying to draw? What is this? This part on the left, what is that? Source. Very good. How about this one on the right? Drain. Thank you. I know you know, but still want to, right? How about this part? Okay, right? Then what is this? Insulator, right? Sometimes I just write Cox, meaning that it is a capacitor, but it's an insulator. Very good. Where does so what happened when we start turning on the transistor? So I'm going to take a cut line here on the surface. This is A, this is A dash. We need to draw the band diagram, right? If you're not very familiar with band diagram, I hope you try your best. But again, this is not the end of the world if you cannot draw it, but still try to draw it. I draw it from the left to right. I'm going to draw it in this way. Sorry, I think better. Why do I draw it in this way? Because the Fermi level here is on top, is N-type. Here is also N-type. And maybe here is, say, 1 volt. Right? I assume this is 1 volt. Remember that I told you earlier, this band diagram is the energy of the electron. So if you have a higher energy, it means your electron energy is higher. Higher electron only gain higher energy with negative potential, right? Because positive times negative is negative. So if I have positive voltage on the right, I pull down the band. Okay? So I have a lot of electrons here on the left. Can they travel to the right based on what I'm drawing here? Can my No. Let's first look at the Fermi-Dirac distribution, which I introduced earlier. Do you still remember that? I say that at the Fermi level, I have about half of the probability the chance of finding an electron above the Fermi level get exponentially smaller. It's just like the dust, right? You see when a truck drive through, you have a lot of dust on the floor, and then it exponentially decrease if you go higher and higher. That's Boltzmann's statistics, but this is pretty similar in the Fermi-Dirac statistics. Okay, so at the Fermi level, it has 50% of chance that it has electron. Above it, it keeps smaller and smaller. So just now you told me that I need to redraw this one. I asked you if there will be any electron, any current. You say no. Why there's no electron? Why there's no current? Can you tell me? Why do you think there's no current? Because you have a high barrier. If I want to go to the other side, I need to go over this barrier. But most of my electron only has this energy. Right? Again, this is the band diagram, right? This is talking about the potential of the electron. You cannot go through. So which part of the electron can go through? I still have some electron that I can go through. This part can go through. I still have current, but very tiny. It's just like the dust on the wall when the truck with all those drive by, right? If you're on the 10th floor, you might still inhale 1 or 2 dust particles. You cannot say that I'm clean, I'm okay. If you're on the 2nd floor, you need to close the window. Lots of dust. Okay? So I still have some current. Now, this is when I put 0 volt at the gate. But what if I try to increase the gate potential? What does it really do? It actually will bring this down. I don't draw it well, however. This is when you have, let's say, 0.5 volt. Note that it's still smaller than the threshold voltage, right? I assume it is smaller than the threshold voltage. Do I have current going through? You still have. Now, then we need to argue. He said a little bit more. Definitely not much, but not a little bit more. Because this one go up exponentially, right? So yes, not much. On the 10th floor, I inhale only 2 dust particles. Now I go to the 5th floor, I actually inhale 1,000 dust particles. Okay? Again, I cannot feel it, but a lot more. So in reality, if you try to plot the IDVG curve, but in log scale, you actually will see something like this. So what am I talking about? This is 0 volt VG. You might have 1 nanoampere of current, very tiny, you don't care. But when I reach 0.5 volt VG, which is the green, then I will get how much? Maybe 10, anything. Let's say microvolt will be safer because 1 microampere. That is 1 million times more current, but still tiny, maybe still tiny. Okay? And eventually you turn it on because this is so low that you are on the 1st floor. Now all the dust just go to go through your window. You've got a lot of dust coming in. Right? So this is the real picture we need to study in this class. If I put this in the linear regime, what would I see? I put it linear. I would see something like this. Exactly what we drew earlier. Need to redraw it. This might be the so-called threshold voltage. I don't see much, and then it goes up. Why? Because here what I'm plotting here, maybe not good to do the dotted line. I'm plotting 1 milliampere, 2 milliampere, 3 milliampere. This is linear scale. Since I'm looking at 1 milliampere spacing, of course 1 micron, which is 1,000 times smaller than the scale, I almost don't see anything, right? That's why I have this cut off. So in your earlier class, this is just, you say, not conducting current, but they are. So why we care about this? Because nowadays you have 10 billion transistors in the chip. And the leakage current we discuss later is also high. It can be in the order of 1 nanoampere. What is 10 billion times 1 nano? What is 1 nano? 10 to the power how much? Minus 9. 10 billion is 10 to the power 10, right? Billion is 10 to the power. That means that even I don't do anything, I turn off all the transistors, there is 10 ampere of current going through already. That's why it matters. That's why nowadays you won't turn off all the transistors at the same time. You actually have some special power saving strategy. Okay? But that is just at a circuit level. And that's why this is relevant. Okay? So now, if you want to model this is in the subthreshold regime. You will model it as e to the power qv divided by nkt. Is this okay? I will discuss more about this equation, but I want you to understand the physics. Now even though you cannot draw this band diagram, you need to have this idea in your brain. You should know that, oh, there's nothing but just a lowering of barrier when you increase the gate voltage. That is the main point. And because of that, you are not going to have an abrupt change because the electron will increase exponentially when you go down the barrier. You actually get more and more electron going through. This is indeed exponentially. Okay? Yeah. Is this the same thing happen as our? Exactly. And that, if you remember, this is similar to the Dow equation, remember? Where's the Dow equation? It's a good question because you should understand this is like diode, right? For diode. If you remember, it is something like this. ID equal to I0, some fundamental leakage, right? E to the power, like VD divided by VTH, which is the thermal voltage KT over Q, right? And then minus 1. When your VD is large enough, this is basically the same. It means you go up exponentially, right? Your diode don't. So that's very good. You also see something like this in diode, right? In linear scale. Usually they say turn on voltage of diode. But you plot in log scale, it is not abrupt. It goes up smoothly. Okay? Good point. And exactly this is a diode. The only difference is that this time I use the gate controller potential. So this is a good question. We should say a little bit more. If it is diode, you actually only have this part. And then you lower the potential, then you get a lot of current going through. So exactly the same physics. The only difference is that in the transistor, you use the gates to control this potential. In diode, you directly connect this to the electrode. That's one thing. Second thing is I have a drain. If this one is not at a higher potential, the electron can go back, so you don't have current. Right? For diode, it's just one direction. Yeah, good point. So they share exactly the same equation. Okay, any questions? I know I'm slow, but it's better to get everything clear, right? So now this is what we said here. Subthreshold conduction. Now you see very clearly. 10 to the minus 12, minus 10, minus 8, minus 6. They go up exponentially, right? Spacing is the same. That's called 2 orders of magnitude. 100 times, another 100 times, another 100 times. That's my dream for my stock. It never happened. Or when it go up, it's really subthreshold. Okay. The main thing I want you to understand here is something called subthreshold swing. What does it mean? It is saying that I want to increase my current by 10 times, right? We keep saying increasing, but the same as reducing. I want to reduce it by 10 times. How much gate voltage do I need to change? That is the main point we are asking here. So for example, here is 10e minus 9. This is 10e minus 10. For example, let's say this is 0.1 volt. It says that if I change my gate voltage by 0.1 volts or 100 millivolt, I can reduce the current by 10 times. Because now we know we do have subthreshold conduction. It's not zero, right? So it makes sense to have this quantity. So subthreshold swing is saying that how much delta VGS, right? This is delta VGS. I need in order to get the current changed by 10 times. So this is ID2 and this is ID1. I change from 10 to the power negative 9 to 10 to the power negative 10. Okay? So what is this? In this case, it is the subthreshold swing SS in this case is 100 millivolt per decade. That is the unit. 1 decade means 10 times. It means I need to change 100 millivolts in order to change the current by 10 times. If what do you think, right? If I have another transistor, I invented another transistor, it is like this. Sorry. Let's say everything is the same. That will be easier for me to draw. I invent another transistor like this. Which one is a better transistor? This one or this one? Do you think? What do you think? Everything else the same, but this one is go down very fast. Which one is better? What do you prefer? For a normal operation. You mean the red one? You want this one? Why? Oh, that's a very good point. He wants to change the ID by controlling the VGS because he has some application he wants to do. So, valid answer. If you answer this in the exam, I will still give you full point, right? But now I'm talking about normal operation, then I need to tell you what it means. We want to have large current when it is on, but no current when it is off, to behave ideally as a switch. What you're saying is correct. For some, we call subthreshold operation. Some people try to bias their transistor as subthreshold that consumes super low energy, although they are slow, but they are very useful. Like because some equipment, like maybe the pacer, right? Pacemaker, man. The pacemaker for your heart. Yes. You don't want to change the battery, right? Once they, but now the technology is very good. People don't care about that. My advisor in my master degree, his PhD was about this. They're like 1980s. That was so critical for the patient. If you have a low power application, then you just do one surgery, you use it for your whole life, right? But still many think that you need very low power consumption. Now, it may be you try to operate in subthreshold. Maybe you try to have a certain slope so you can control very good. But now I'm only thinking about digital. I want it to have a large current and small current when it is off. Large current when it is on, small current when it is off. Which one is better? The red one, right? Yeah, because I can turn it on so fast, right? So ideally, we want a small subthreshold swing. The best is what? What is the best subthreshold swing? Meaning that how many voltage? Yeah, he says that what is that? Vertical. So when it is vertical, what is the subthreshold swing by definition? Think carefully. By definition, is how much voltage you need to increase by 10 times, current by 10 times? Zero. Yeah. So this is something always confuse people. Okay. Ideally, I want 0 millivolt per decade. This is the ideal switch. Okay. Now, good. So it turned out that that is not the case, and this is the equation. You see that it depends on the temperature. Do you understand why it depends on the temperature? Larger temperature has a larger swing. It means I need to apply more voltage in order to turn it off. Look at this figure. Maybe you don't know, I did not explain. This distribution is for a certain temperature. If you go to lower temperature, you get less and less electron on the top. This becomes sharper and sharper. At 0 Kelvin, it is just a box. So you start with no electron, and suddenly with a lot of electrons, where we cross over the Fermi level. Okay, so we don't derive it, but the point is that it depends on temperature. So for example, at 300 Kelvin, which is the room temperature, you might get 60 millivolt per decade for your device. But if you cool it down to 3 Kelvin, then you will scale by another 100 times, which is 0.6, right? 0.6 millivolt per decade. This is a big deal if it works. If it works. If it doesn't work, I will tell you later why it doesn't work. Because if I have 0.6 volt, let's say the threshold voltage is 0.6 volt. In order, when I go to 0, then it will decrease by 10 decades, right? Because I have 1060 millivolt. But if I use this one, I'm going to decrease by 1,000 decades because I have 1,000 more, right? So this is 10 to the power 100 less leakage than the room transistor. So just look at this. You see that at 0.5, this one has a very big difference already, right? At 0.5 volt, I only have this leakage, but the room one has this one. Is this okay? So unfortunately, I won't spend time to explain this end, but we need it later. Let me just finish this 2 slides. I know almost time. It's time, right? Just finish this slide. This is what I want to tell you. So ideally, I have this one is room temperature. When I go to room temperature, lower temperature, it has a lower subthreshold swing. The off current reduces a lot. The power consumption of a chip depends on the switching power and the off-state power, right? It is off with VDD, you have this consumption. Unfortunately, in theory, this subthreshold swing reduces with temperature in this way, straight line. But unfortunately, it's saturated. I cannot get 0.6 millivolt per decade. It actually saturates between 10 to 20 millivolt per decade. Okay, that is a physics. So this is the subthreshold saturation. Why is that? That is because people think that there might be some band tail here. It's not sharp, but because of time, maybe let me just do it next time. Okay, we can stop here. I will continue next time.